In this video, we're going to solve trigonometric integrals. So, all right, first problem, we want to find the indefinite integral of sine squared x times cosine cubed x dx. Okay, and so with integrals involving sines and or cosines, either a sine to a certain power by itself, a cosine to a certain power by itself, or some multiplication of a power of sine with a power of cosine, you're looking for odd powers. That's the first thing you're looking for. If you've got an odd power of a sine by itself, an odd power of a cosine by itself, then you can solve that using a standard method. But if you're multiplying two powers, then you want to look for which one is the odd power. If one of them is an odd power, then you can use that standard cookbook method. And in fact, the only remaining cases are that if you've got an even power of sine by itself, an even power of cosine by itself, or you're multiplying powers of sine and cosine to where they're both even. And actually, there is a cookbook way of solving those as well, using the double angle identity. And so we can actually, for all cases of sines, cosines by themselves, or multiplying powers of sines and cosines, there's a cookbook way to solve it. I think in the video where we went through the textbook, I might have said that the cookbook outline didn't cover all cases of combinations of sines and cosines or sines and cosines by themselves, but I was mistaken. We have that nice plug and chug method for all cases, but that's not the case for like combinations of tangent and secant. The kind of cookbook outline didn't cover all cases. For the remaining cases, it was more of kind of you have to figure it out on your own with integration by parts and just playing with trig identities. And for combinations of cotangent and cosecant, I think it would be similar to tangent and secant, to where you can use those plug and chug methods, but it doesn't cover all cases. And the reason why combinations of sines and cosines it covers all cases is because the derivatives are a lot cleaner in this case, like the derivatives in integrals, being that the derivative of sine x is just cosine x, and the derivative of cosine x is just sine x with a minus sign, which minus signs or constants don't make it more complicated as far as integration. But that's not the case when it comes to tangents and secants, and cotangents and cosecants. All right, so we see, here we see we've got an odd power of cosine. And so the idea is what we're going to do is we're going to take one of the cosines from the cosine cubed and then so we've got a cosine x dx, and then we're going to express the remaining function in terms of just sines. And how we're going to do that, we're going to use the trig identity sine squared x plus cosine squared x is equal to 1. So okay, and so what this allows us to do is this is set up to where we can make a u substitution. U is equal to sine x, therefore du is equal to cosine x dx. And so making this substitution, we've got u squared 1 minus u squared du. And we can solve this. So this is u squared minus u to the fourth du. Okay. So we can separate this into two separate integrals. Okay. So there's the integral of u squared and u to the fourth, and now just substitute the u back in. So 1/3 sine cubed of x minus 1/5 sine to the fifth of x. So there's the capital F of x. We just need to add plus c. Okay, so we've got two odd powers here, so we can just pick whichever one we want to separate a factor from. And to me, I'm thinking use the smaller power to separate the factor, because the one that we separate the factor from, we're going to be turning into like 1 minus something squared. I mean, it probably doesn't matter, but that's kind of what my gut instinct is telling me. So this is okay, so this is and now we've got, so cosine squared of theta squared, right? So that's 1 minus sine squared theta squared, right? So you see what I mean? My thoughts are that if we would have done, separate out a sine theta from sine to the 7th, then we'd be dealing with sine to the 6th, which would, it'd make this a little more complicated, but you could still do it. All right, so now we can make the u substitution. That u is equal to sine theta. So du is equal to cosine theta d theta. And so the idea is, again, what's happening is that with the odd power, you can separate out, like a cosine theta d theta, and then you're left with, you can turn it into just a function of sine theta. And that's what allows you to make the u substitution, okay? And so what we have is, and you don't have to update the limits of integration based on the substitution, but to me, I like to do it. It makes it easier. So, okay, when theta is equal to 0, u is equal to 0. When theta is equal to pi over 2, sine theta is equal to 1. All right, so we've got u to the 7th, 1 minus u squared du. Okay, so, all right, 1 minus u squared plus 4u to the 4th du. Okay, so u to the 7th minus 2u to the 9th plus 4u to the 11th. So, okay, we've got 1/8 u to the 8th minus, so 1/10 u to the 10th times 2, so it'd be 1/5 u to the 10th, is that right? Bring down the 10, you get 2, yep. Okay, and then 1/12 u to the 12th, and then times 4, 1/3 u to the 12th, is that right? Yeah. Okay, and this is going from 0 to 1. When you plug in 0, this goes to 0, so we just plug in 1. You see, this is really nice, this updating the limits of integration. 1/8 minus 1/5 plus 1/3. Let's just use a calculator here. So 1/8 minus 1/5 plus 1/3. 31 over 120. Okay, so I messed something up, and where it looks like, I don't know why I put 4u to the 4th. That's just positive u to the 4th. Right? Minus u squared times minus u squared is just u to the 4th. So this would be 1/12 u to the 12th. So this is just u to the 12, or 1 over 12. So 1/8 minus 1/5 plus 1 over 12 is 1 over 120. All right. So when you see these two t's here, and my thought is, you can, you might get caught up in thinking, oh, we're going to need to use like a half angle identity, or maybe this is a double angle identity. But if you notice, if we just say u is equal to 2t, then du is equal to what? Du dt is equal to 2, so du is equal to 2 dt. So 1/2 du is equal to dt. And so we can turn this into a regular trigonometric integral. And then du, and then we bring out this 1/2. Okay? So now we just have a regular trigonometric integral, and we look and see we have one of these is odd. It wouldn't matter if both are even, but the kind of the easier standard way of solving these is when you have a power of a sine or a cosine that's odd. And so what you do is, because you have one that's odd, you take out a sine here, and you get sine to the 4th of u, cosine squared of u, sine u, du. And then what this allows you to do is you make a substitution of either, well, it's going to be z. We'll use another, we can't use u, but a substitution to where the derivative of that variable is equal to this sine of u du. And so we're going to say z is equal to cosine u. So that dz is equal to minus sine u du. Therefore, minus dz is equal to sine u du. There you go. And so what we have is, so sine to the 4th of u, or no, we don't do that. I jumped the gun a bit here. We first want to convert we have sine u du, but we want to convert this to where outside of the sine u du, we have just a function of cosine. So we're going to use here, for sine to the 4th, we're going to use the sine squared x plus cosine squared x is equal to 1 formula. So we had sine to the 4th of u, which is sine squared of u squared. So 1 minus cosine squared of u squared. Then cosine squared of u, then sine u du. Now this substitution is going to work because z is cosine u, so we've got 1 minus u squared squared, and then we've got u squared, and then what do we have? Sine u du, that's minus dz. Oh, wait, this is z. We have 1 minus z squared. Squared, z squared, and then minus dz. So I'm going to put dz and then bring the minus here. Okay, so 1 minus z squared is 1 minus z squared minus 2z squared minus z squared times minus z squared is plus z to the 4th. Z squared dz. Okay. So z squared minus 2z to the fourth plus z to the sixth dz. Okay, so we've got minus 1/2 times the integral of all of these, which is, so 1/3 z cubed minus, and this would be 2/3 z, or no, this would be 2/5 z to the fifth, and then 1/7 z, looks like a z, 1/7 z to the seventh. Okay, so let's do it like minus 1/6 z cubed plus 1/5 z to the fifth minus 1/14 z to the seventh plus c. And that is the integral. Oh, wait, no. I'm messing up here. We got to substitute back. So, okay. Minus 1/6 cosine cubed of u plus 1/5 cosine to the fifth of u minus 1/14 cosine to the seventh of u. Okay, but u is equal to 2t. So minus 1/6 cosine cubed 2t plus 1/5 cosine to the fifth of 2t minus 1/14 cosine to the seventh of 2t. And that is the integral, or plus c. Okay, so we have just a cosine to a certain power, and remember, we can with even powers or odd powers of just sine or cosine, we have cookbook methods to solve this. If this were just a power of a tangent or a secant, then we can still solve it, but we don't have that nice cookbook guideline to solve those. Okay, and when it comes to even powers of sine or cosine, either just a cosine to an even power, just a sine to an even power, or a sine to an even power multiplied by cosine to an even power. To solve it, we need to use the corresponding half angle identity. So the half angle identity here is cosine squared theta is equal to 1/2 1 plus cosine 2 theta. Okay, so if we apply this trig identity, okay, you can see how this is going to be easier to solve. You know, when it comes to integration, it's easier to work with, like, you know, a cosine 2 theta. Like, usually, in most circumstances up to this point in math, we want to solve whatever we're trying to solve for. We want to get out of this. We want to separate this into just like cosines of thetas. But with integration, this is, you know, if we can get this by itself, then it's easy to integrate. So this is, we could separate this into two separate integrals. Okay. All right, so okay, so 1/2 times just pi over 2. And then we've got the integral of cosine 2 theta is 1/2 sine 2 theta. And then we're evaluating this from 0 to pi over 2. So pi over 4, we could take out that 1/2. And it's just sine of 2 theta from 0 to pi over 2. Okay. Sine of 2 times pi over 2, that's sine of pi, which is 0. And then sine of 0 is 0, so this is just pi over 4. Okay, so we have an even power of just a cosine. We're going to be using the double angle identity. Cosine squared of x is equal to 1/2 1 plus cosine 2x. Let's start by getting rid of this 2t. So du is equal to 2 dt. 1/2 du is equal to dt. So when t is equal to 0, u is equal to 0. When t is equal to pi, u is equal to 2 pi. Cosine to the 4th of u du and bring a 1/2 out. All right. So we've got 1/2 1 plus cosine 2u. Okay, but then all of this squared. Okay, so 1/2 squared is 1/4. Bring out the 1/4. Okay. So we've got 1 plus cosine 2u plus cosine 2u plus cosine of 2u times cosine of 2u is cosine squared of 2u. Okay, so let's actually make another substitution. Let's say that z is equal to 2u. Therefore, dz is equal to 2 du. 1/2 dz is equal to du. All right. When u is equal to 0, z is equal to 0. When u is equal to 2 pi, z is equal to 4 pi. I don't mind making these another substitution because we're not gonna have to substitute back, so it's not going to be that complicated because it's a definite integral. Okay, so 1 plus 2 cosine z plus cosine squared of z dz. We have to bring out a 1/2. So this is 1/16. So we've got 1/16, and then we can separate this into separate integrals. 0 to 4 pi dz plus 2 0 to 4 pi cosine z dz plus 0 to 4 pi cosine squared z dz. Okay, so now this cosine squared here, to solve this, we need to use the half angle identity. So we've got 1/16, and then this would just be 4 pi. okay, plus 2, and then this is going to be sine z evaluated from 0 to 4 pi plus, and then we've got 0, 4 pi. We could take out the 1/2, and you've got 1 plus cosine of 2z dz. Okay, now we can erase everything else because, we don't have to back substitute because this is a definite integral. So we've got 1/16 4 pi plus, so here sine of 0 is 0, sine of 4 pi is 0, so that goes away. Then we've got 1/2 integral 0 to 4 pi dz plus 1/2 integral 0 to 4 pi cosine 2z dz. So 4 pi, and then here we've got 1/2 times 4 pi plus, okay, the integral of cosine 2z is 1/2 sine 2z. So let's bring out the 1/2, so 1/4 sine of 2z from 0 to 4 pi. This is 0, right? Yes. So we've got 1/16 4 pi times 4 pi plus 2 pi. 1/16 times 6 pi. Three-eighths pi. Okay, so we've got two even powers of sine and cosine. For this, we need to use the half angle identities. So sine squared of x is equal to 1/2 1 minus cosine 2x, and then cosine squared x is 1/2 1 plus cosine 2x. Okay, so and you can see why this works out. It's because both of these involve strictly a cosine. So sine squared of x is 1/2 1 minus cosine 2x, and then cosine squared of x is 1/2 1 plus cosine 2x. So 1/4 okay, and this is like an a minus b, a plus b, so we're going to get like, it's going to be 1 minus cosine squared of 2x should be what it is. So 1 times 1, oh, this goes from 0 to 1 times 1 is 1 plus cosine 2x minus cosine 2x, and then minus cosine squared 2x. Yeah, so one minus cosine squared 2x. So this is 1/4 minus okay, so let's do a u substitution here. U is equal to 2x, du is equal to 2 dx. So 1/2 du is equal to dx. So we've got 1/4 times pi over 2 minus 1/4. Okay, when x is equal to 0, u is equal to 0. When x is equal to pi over 2, u is equal to pi. Cosine squared of u du, and bring out a factor of 1/2. Okay, so we've got pi over 8 minus 1/8. And so here we need to use the half angle identity. So 1/2, 1 plus cosine of 2u. So we've got, we'll have 1/8 and then just 1/2 du. So 1/16, like that. Then we'll have another 1/2 that we can take out. And then like that. So we've got minus 1/16 pi minus the integral of cosine 2u is 1/2 sine 2u. Bring out the 1/2. Zero to pi, so sine of 0 is 0, sine of 2 pi is 0. So we're left with, this is 1/8 pi minus 1/16 pi. So 2/16 pi minus 1/16 pi is 1/16 pi, pi over 16. All right, this one is, they kind of throw you a curveball here because it's not of that general form, some power of sine, like an integer power of cosine or sine times an integer power of sine or cosine. But the key here is to remember that, so that what's important is that we have an odd power of sine or cosine, because what they're testing you on here is if you understand the general idea of what we're doing with like to solve these, then it doesn't matter that this is like cosine theta to the 1/2 power, because like, okay, we get sine squared theta, sine theta d theta, okay? And now what's the idea then? Because this is an odd power of sine, we're left with this sine squared, or an even power of sine, and we could make the trig substitution of 1 minus cosine squared theta. And so what do we have? We've got sine theta d theta and then just some function of cosine theta. So that's going to allow us, we can make the substitution that u is equal to cosine theta, and therefore du is equal to minus sine theta d theta. So minus du is equal to sine theta d theta. There it is. And so what we have is, so cosine theta is u, we'll put u to the 1/2, 1 minus u squared, and then du with the minus sign. And so we can solve this, right? This is u to the 1/2 minus 2 plus 1/2 is, so 1 over 2 plus 4 over 2 is 5 over 2. So we have and then plus all right, 1/2 plus 1 is 3/2. U to the 3/2 over 3/2 is, so we got minus 2/3 u to the 3/2. All right, 5/2 plus 1 is, so 5/2 plus 2 over 2, that's 7/2. U to the 7/2 over 7/2 is 2/7 u to the 7/2. Okay, so let's put this to the positive first here. So we've got 2/7 cosine squared theta to the 7th power minus 2/3, or no, wait, that's not right. It's the square root of cosine theta. I mean, I'm just going to do it like this. I'm going to say 2/7 cosine theta to the 7/2 minus 2/3 cosine theta to the 3/2, like that, okay, plus c. Okay, so here, we didn't cover anything like this specifically in the textbook, like combinations of cotangents and cosines, but the idea is what we learned in the textbook, the concepts, we can apply that here. And so, all right, we know that cotangent is cosine over sine. So cosine x over sine of x times cosine squared x dx. Okay, so cosine cubed of x over sine of x dx. All right, so we get this here. But wait a minute, we didn't talk about this. We didn't cover a case like this in the textbook. But what they're testing you on is that we can use the exact same concept that we used in the what the textbook demonstrated. What do I mean by that? Well, look, we've got an odd power of cosine. So let's do the same technique. We have cosine squared of x over sine of x cosine x dx. So, okay, if we say u is equal to, well, no, we don't do that yet. Next we say cosine squared of x is 1 minus sine squared of x and there we go. So now we say that we have cosine x dx and then some function just of sine of x. So u is equal to be sine of x, and du is equal to cosine x dx. So we've got 1 minus u squared over u du. You see? So we've got see? So this is natural log of the absolute value of u minus 1/2 u squared plus c. But now we need to bring back substitute for what u is. There we go. Okay, so, again, we have an integral that doesn't exactly follow one of the example problems that were demonstrated in the textbook. And so, but what you want to do is you still want to use the same principles that were taught. And, in general, you just want to take a look and see, okay, like think about the trig identities. If you have an integral that doesn't follow one of the exact templates that were taught, first you can think about the trig identities. And so, I see a sine of 2x here, and I think about that half angle identity, so we can relate this to or no, we can't, because the half angle identities only work with a cosine of 2x. But so what we're trying to do is we would like to potentially create a cosine x dx, right? And if you think about, there's trig identities that there's a trig identity that's like its sine of 2x is something with a cosine x sine x. Like its sine of 2x is equal to some like 2 times sine x cosine x, which that would be potentially useful here. So the identity is that sine of 2x is equal to 2 sine x cosine x. And this is useful because when we make the substitution, we get a cosine x dx and then just some function of sines of x's. And that's the principle that, the main principle that was used in the textbook. You want to, it doesn't matter what the form of the integral is that's given to you. If you can in any way, no matter what it is, get a cosine x dx, and then outside of that, just some function of just sines of x's, then you can make a u substitution and simplify the integral. Okay, so we can say, making this substitution, this is times 2 sine x cosine x dx. And so bringing out that 2, you've got, and simplifying, sine cubed of x cosine x dx. And there we go. That's perfect. U is equal to sine of x. Du is equal to cosine x dx. So we've got the integral of u cubed du. So 2 times 1/4 u to the 4th. 1/2 u to the 4th. Okay, so sine to the 4th of x over 2 plus c. That's it. All right, well, we've got an even power of sine, okay, and then, but there's no other odd power of like a cosine. All right, so, I mean, think about the half angle identity. So sine squared of t is equal to 1/2 1 minus cosine of 2t. Maybe that'll help us. Let's just try it out and see. So t, and then let's take out the 1/2 1 minus cosine 2t dt. So this is t minus t cosine 2t dt. Okay, so I'm not sure if this helps us too much. Okay, so, you know, we might be able to solve this with integration by parts, but let's see if maybe they were wanting us to do something else. So, yeah, I don't think there's another trick here that I'm missing. So, yeah, I mean, let's just do integration by parts. So this is going to be 1/4 t squared. All right. And then, well, okay. Let's just do, okay. So cosine is easy to integrate and differentiate. So is t, but if we could choose, we'll differentiate t. Okay. So dv is cosine 2t. So v is equal to 1/2 sine of 2t. So this looks like it's going to be one of those where we end up with this same integral in the formula. So, all right, u times v minus integral of v du. Or no, okay, we're not going to have to do this. We're not going to end up with t. This actually simplifies. So, okay. So we've got, and then this is going to be, the integral of sine 2t is minus 1/2 cosine 2t. So plus 1/4 cosine 2t. All right. So that integral is 1/2 t sine 2t plus 1/4 cosine 2t. All right, so this is 1/4 t squared minus 1/4 t sine 2t minus 1/8 cosine 2t. There you go. That's it, plus c. All right, and so in the next video, we're going to work with combinations of tangents and secants.